All right, so we're going to be talking about the types of bonding here. So why do atoms bond? And as he said in the video too, it's to achieve this lower energy, but the lower energy configuration is really the stability. And looking like a noble gas and having that full octet achieves that lower energy for the atom. Okay? When atoms bond, they form ionic compounds or covalent compounds, and sometimes molecules. Covalent compounds share electrons, but we do have some that aren't compounds because we have our diatomic molecules that are single elements, but they do share electrons to form the twins like Br2 and O2 and things like that. But the whole idea here is to make sure they have that magic number of 8. Most elements mimic the noble gases that have 8. There are a few at the top, though, that remember only require 2 to look like helium. Okay? So it's all about achieving stability, that lower energy configuration. Ionic compounds are formed when you have a metal and a non-metal reacting. And it's about the electronegativity difference that creates the ions, because you have the less electronegative element, which is the metal, reacting with the more electronegative element, which happens to be the non-metal, and the electronegativity difference is greater than 1.67. Okay, for example here, and you can write that in the space there, sodium at 0.9 and chlorine at 3.0, if you subtract them, the difference is going to end up being 2.1. 2.1 is a greater value than 1.67, and therefore this falls into the ionic part of the spectrum and indicates a full transfer of the electron as well, whereas there is the ones where it's more polar versus a full transfer of electron. And as he also noted, the ionic compounds form these crystalline structures. They are lattice structures. They are based on some kind of geometric pattern. In this case, sodium chloride shows more of a cubic pattern here of the repeating positive and negative charges shown here, and it kind of looks like the Tinker Toys if you're putting them together. But the chlorine, which is negative, and then in the middle of that would be positive sodium, and they just have this repeating unit, and it forms this nice big crystalline structure. We're going to get into that repeating unit. That's called the formula unit, which we used when we were doing the calculations with Avogadro's numbers, because the ionic compounds really are repeating units and form crystalline structures, these lattice structures. Ionic bonding formed when the transfer of electrons occurs. When the transfer of the electrons occurs, now we have charged particles or ions. The charged particles, like sodium being the metal and being the cation, giving away the electron, losing the electron to the chlorine, which happens to be the anion, the negatively charged one that gains the electron. And then it forms an electrostatic attraction. The positive and negative charges on these ions is actually what forms the bond. It's a Coulombic attraction. He also talked about that in the video about Coulomb's law, although we will not be calculating that here in honors. That is something that they do in AP. And it actually, the charges and the distance will determine the strength of the ionic bond, and certain ionic compounds have stronger bonds than others, although in general, ionic compounds have the strongest type of bonding, very high boiling and melting points. We're talking like to melt sodium chloride, it's like up there in the 800-degree range. So it's very, very, very high in order to melt these things. There's very few substances that would be stronger than ionic compounds, like, few network covalent solids like the diamond, but those are rare cases. Okay. So here we show the sodium forms the plus, the chlorine forms the minus, and now because of the opposite charges, they attract to one another, forming the new compound. And it's just going to repeat in a pattern and build the crystalline structure. Now, you do not need to write this down, but this is the Bohr model version, showing here sodium atom with its 1 valence electron in the 3s here, using our electron configurations from last unit. It gives it away. When it loses that 1 valence electron, it now, oops, went ahead a little, there we go. All right, the sodium ion is formed, and now it has the 2p6 completely filled, and it now has the same configuration as neon. So the Bohr model situation, we're not going to be drawing a lot of these because they add the extra energy levels in there that we really don't need to waste our time with, but the general idea is now it's mimicking neon, and it has a stable configuration, but it does have a +1 charge. And here in the chlorine atom, did a modified configuration here, just kind of showing you the end here with 3p5. The 3p5, of course, now once it gains the 1 electron, we'll complete that and make it 3p6. Oops. And the 3p6 now, the outer energy level, the 3, the S2, and the p6, have now completed it, and chloride looks like argon. But it has a -1 charge, and by having that charge, now it can attract to positive things. Here is another version showing you the sodium and the chlorine. Sodium gives away the electron, and now we have our 2 charged particles, positive and negative, and they now attract to one another, and they're both stable because they both have noble gas configurations. And up there is showing you the nice crystalline structure of the sodium chloride. Now, how we're going to represent it when we draw them, we're going to use Lewis dot structures. So for sodium here, I'm going to draw a symbol, and I'm going to put the valence electrons around it like I did for unit 3. How many valence electrons does sodium have? We need to know our valence electrons for this unit, and we need to know our generalized charges of our groups. And sodium is an alkali metal, and yes, it has 1 valence electron. So how many dots am I going to put around it?
1 dot.
1 dot, thank you, good. Now, chlorine, Cl, halogen, group 17 or 7A, how many dots is it going to have?
7 dots.
7 dots, there we go for our chlorine. Okay, so in order to show this, we would show the transfer here using an arrow. The sodium's giving up its 1 valence electron over to the chlorine, which is now going to gain it. So sodium ends up getting a +1 charge. Over here, the chlorine is going to gain the 1 from the sodium. I'm going to use red to represent the electron that was gained from the sodium. And it's going to have a charge of -1. And here, the +1 and the -1 should add up to 0. I'm sure you're probably seeing that in your POGL that you've been doing, where the charges of the compound have a net overall charge of 0. But the positive and negatives from both different species in the compound should add up to 0. In this case, too, we have 1 sodium to 1 chlorine. Our overall formula for sodium chloride would just be NaCl because it's 1 of each, representing the lowest ratio formula unit for this particular compound. And then the NaCls would repeat in the pattern, the cubic pattern you saw in the lattice structure. However, this is very simplistic, probably the most simplistic form of an ionic compound, because we know that not all of them are going to end up being a 1-to-1 ratio. For example, if we are trying to bond magnesium with the chlorine, we have another problem here. Magnesium, being an alkaline earth metal, is going to have 2 valence electrons. Chlorine is still going to have 7. So, this magnesium transfers 1 of its electrons to a chlorine, and there's only 1 chlorine available. We have a problem. Why is that a problem? Magnesium is still unstable because it still has 1 extra valence electron that it needs to get rid of. So, to solve this problem, instead of only bonding with 1 chlorine, we're going to bond with 2 chlorines. So the magnesium can transfer over both electrons. In this particular case, the magnesium ends up being a +2 charge because it gave away 2 electrons. And each chlorine has now gained 1 from the magnesium. I'm going to note those ones that they gained from magnesium in green here. And each of the chlorines has a -1 charge on them. And if you still look, we have a +2, we have a -1, and a -1. That should still all add up to 0. And it does, it adds up to 0. But in this particular case, instead of having a 1-to-1 ratio, we have 1 magnesium for every 2 chlorines. And so if we wrote out the formula for this one, it would be MgCl2. You would need 2 chlorine ions for every 1 magnesium ions. And therefore, this repeating pattern isn't going to be a cubic relationship, but it'll be another geometrical pattern. If you want to look into the lattice structures, you can. They are different geometrical patterns based off of their ratios. So keep that in mind. We're not going to go into a huge amount of detail of the solid crystalline structures of ionic compounds, but you can Google any of them at any time. All right, covalent or molecular compounds. They're formed between nonmetals and nonmetals, and as he stated in the video, sometimes it can be a nonmetal with a metalloid. They will share electrons with nonmetals and form covalent or molecular compounds. 2 elements with similar electronegativities where the difference is equal to or less than the 1.67 value. And if we're looking at an example here with carbon and oxygen, carbon is 2.5, oxygen is 3.5 from their electronegativity values. Remember, electronegativity was one of those periodic trends where the atom has the ability to attract electrons in a chemical compound. Ones with high electronegativities are very reactive, like fluorine is the highest most electronegative element on the table. Oxygen is second to fluorine in this case. But if you do the difference here, the difference is only 1. 3.5 minus 2.5 gives you 1 as the difference, which is less than 1.67. So it puts it in the covalent category. Now we're going to get into the polarity stuff, which he touched on in the video, the nonpolar and polar stuff later on in the unit when we get past ionic compounds and start talking about covalent and drawing the Lewis dot structures for covalent compounds. But this is just a generalized PowerPoint and information on the different types of bonding. Formed by sharing of electrons. They don't always equally share, but they do share. It's not a transfer, it's a sharing. And the molecules can be formed 2 or more atoms bond covalently. So here in this case are diatomic molecules, which are molecular elements. But between the 2 Br atoms, they share a pair of electrons, so Br2 is still considered a molecule, even though it's not a compound. Remember, the definition of a compound, it must have 2 or more elements in it. In this case, our diatomic molecules are diatomic elements, but they do share electrons to be formed, to be their twins. Now here, represented by Bohr model diagrams, we'll also be using Lewis dot structures later. So for instance, methane could be drawn like this with a Lewis dot structure. Each line showing a pair of electrons being shared. Here, water, you've probably seen before, drawn. Now, the water he touched on, and you know this from biology, is a polar molecule. The oxygen has a higher electronegativity value and the electrons spend more time around it. So it actually creates a partial charge over here, partial charge over here. So that's why we have 2 poles to our molecule. We'll get into polarity later, but do know that they don't always share equally. However, in methane, the electronegativities between the carbon and the hydrogen are very similar. So they share very equally, so methane would be considered nonpolar. The electronegativity difference is not that high. Methane, if you're unfamiliar with it, is natural gas and what pretty much comes out of our outlets and our stoves and things like that. But it's showing you here in this particular diagram that one of the electrons came from the hydrogen, and the ones that are X's here came from the carbon, but when they share between them, the carbon now has 8 and looks like neon, and each hydrogen has 2 that looks like helium. Stability, the name of the game here, stability. Metallic bonds. Why can we have sheets of aluminum foil or copper wires where it's just atoms of the particular metal? Well, they have something called metallic bonds, and they're a little bit interesting in the way that they do their bonding. There are electrostatic attractions that occur between positively charged metal nuclei and the delocalized electrons. The valence electrons of metals have this ability to delocalize and detach, and they're sort of like this sea of electrons where they kind of distribute around the different positive nuclei. But having these electrons being able to have more of a free flow is why they can conduct electricity, because you have electrons available for the conduction process. And they're not just being attracted into the cloud there. They're available and can be conducted. So keep in mind, so when you pull out a sheet of aluminum, that's just a bunch of aluminum atoms that are metallically bonded to more aluminum atoms. This also helps with the other metallic properties of malleability and ductility, being able to form wires and be pounded and molded into different forms. Okay? Because these electrons behave the way they do for the metals. Good? Yes? No? All right, what happens when we put compounds in water? Well, ionic compounds, when you put them in water and they dissolve, they form something called electrolytes. Electrolytes are ions in solution. And we'll get into the process of how they dissociate later on when we get to solutions. And it is a process of dissociation, not just dissolving. The water polar molecules end up surrounding the sodiums and the chlorine and pull them apart, basically. That's why we say it's a dissociation, because the sodium has to completely break apart from the chlorine in order for it to dissolve into the water and you can't see it anymore. So they separate, okay? And now you have these free ions floating around in the water. So they have the ability to conduct electricity. They have charged particles in the water, and if you run an electrical current through it, then it will be able to conduct electricity, and this is primarily the reason why if you're swimming in the ocean in a lightning storm, that's very dangerous, because lightning strikes the water, it will be able to conduct it. Same thing for a swimming pool. Swimming pools have lots of dissolved chemicals in them that have ions because they're trying to kill the bacteria and algae from growing in the pools. So lightning storm, swimming, not very good thing to do together. Covalent compounds are called non-electrolytes. Like sugar. Sugar can dissolve in water. Sugar is a covalent compound. It has lots of carbons and hydrogens and oxygens in it, all non-metals. And what it does is it dissolves too. The water surrounds those individual particles, but the sugars themselves are not ions. They don't have charges on them. So they're not going to conduct any electricity. So you could go swimming in a pool of sugar water, but then of course you'd be really sticky afterwards. And you wouldn't want to probably be there the next day when all the algae and bacteria is growing in it. But it's not going to conduct electricity. All right, so let's put it all together and go through the chart. You can use this as a good study tool. Types of elements, a metal and a nonmetal for ionic, covalent, 2 nonmetals, and of course metallic is going to be only metals. The electron behavior. Ionic is going to do what with their electrons? What's the key word? Transfer. Very good. Transfer those electrons so they can form charged particles or ions. Covalent compounds do what? Share electrons. And metallic, what happens with their electrons? Anyone? They're the sea of electrons. They delocalize, remember? Then they can go around any of the nuclei and have more of a free-flowing nature. Now, they're all held together, yes, by electrostatic attractions. The ionic compounds have a full charge on them, so their electrostatic attraction is quite high in terms of strength. Covalent compounds, you're sharing the pair of electrons between the two nuclei and the electron clouds. So you do have some attractive forces, like he said in the video as well, that each nuclei is attracting electrons from the other atom. So there is some electrostatic attraction in there while they're sharing. And then, of course, the metals, the sea of electrons, you have the positive nuclei and the electrons kind of flowing around them. They're also positive and negative means electrostatic attraction or Coulombic attraction. That's the real fancy word, as he was talking about with Coulomb's law in there. The electronegativity difference, greater than 1.67 for ionic, equal to or less than 1.67 for covalent, and metals, really like an aluminum's electronegativity minusing another aluminum's electronegativity is just going to give you zeros. So it doesn't really apply here for the metals, because they're just a bunch of metal atoms that are together. Sheet of aluminum is just a sheet of aluminum atoms. Now, we know ionic compounds, is if you look in your cupboard and find your salt, are going to be solid at room temperature in a lattice or crystalline structure. How about most covalent compounds, though, that you know of at room temperature? Where are they going to be? What kind of physical state? Gas or liquid, and water being the primary example of the liquid, but just our atmosphere, the nitrogen, oxygen, and other gases in our atmosphere, telling you that all those are covalent compounds, are usually in the liquid or gas phase. There are a few covalent compounds that are solid, of course, but the majority of them are going to be more in the liquid gas phase. And metallic, of course, are solid. You know that most metals are solid at room temperature, mercury aside. And by their physical states, we should be able to ascertain or make a prediction about their melting and boiling points. If ionic compounds are solid at room temperature, what should that say about their melting and boiling points? That they're high, good. Remember, solid structures have forces holding them together in place. As a solid is a repeating, orderly structure, you have to break those forces in order to get it to spread out and become a liquid. So if it's holding together and is a solid at room temperature, that means you're going to have to add lots of energy to it. Some are higher than others. You know, to melt some metals, sometimes it's in the thousands. You know, the sodium chloride salt is in the 800s in terms of temperature. Now, covalent compounds like water, the melting point of water is 0 degrees, which isn't very high. The boiling point of water is 100 degrees Celsius, which seems like, oh, that's hot because if we touch it, yes, we'll burn. But in comparison to sodium chloride, which is more in the 800 range, this definitely would be considered lower. And of course, like I just said about metals, they're really high to melt them down to, I mean, mine is trying to turn them into a gas with the boiling point. That'd be super, super high. Now the last one down here is electrical conductivity. When you dissolve it in water, ionic compounds will conduct. It also says molten there, and like I said, it will conduct if you melt it down to a liquid, but melting sodium chloride or an ionic solid down to a liquid, it's going to be like lava. It's going to be that hot. So we call it molten. Covalent compounds do not conduct. And metals, of course, are excellent conductors of electricity. Just in and of themselves, they have those movable electrons, those flowing electrons. Are there any questions? Basic gist of the 3 types of bonding. We're going to really focus on the ionic naming and formula writing now, and later on in the unit we'll get more into the covalent. Metallic bonding, not a whole lot here except for the basic definition and the properties of metals. We won't be going much further into that. All good?